Well, hello again. In this example, you will learn how to perform moment distribution of a frame which is prone to side sway. This is the frame we're going to consider, and as you take a look at the loads that are being applied, you can most certainly understand that joints B and C will definitely shift to the right, and that is known as sway. Before we get into the analysis, let's make sure we understand what we're looking at. Moment of inertia of all members is 2,400 inches to the fourth. Here's the modulus of elasticity. The frame width is 30 feet, or 360 inches. And the frame height is 20 feet, which is 240 inches. Now, we don't necessarily know how to analyze a frame with sway using moment distribution, but we do know how to do it if no sway occurs. So what we will do is we will go ahead and lock it against sway. And then we can proceed with the moment distribution analysis the way we always would. So first step of that is lock the joints against rotation and then solve for the stiffness factors and distribution factors. So for KBA, it will be a 4EI over L, and for KBC, it will also be 4EI over L. So this would be 1/5, this would be 2/15, and we can use that to then get the distribution factors. For BA would be 1/5 equals 0.6, and DFBC is equal to 1.0 minus 0.6 is equal to 0.4. And if you recognize that the structure is symmetric, then you will know what the distribution factors are for CB and CD. Next thing I want to do is compute the fixed end moments. And from a beam chart for a fixed end member with the point load in the middle, the max moment at the end is PL over 8. So for this one, we'd get 60 kips, 360 inches, all over 8 is equal to 2,700 kip inches. And for this one, 50 kips, 240 inches, all over 8, and that will be equal to 1,500 kip inches. I'm going to go ahead and sketch those on these diagrams. And now with that information, remembering that a clockwise moment is considered positive, we can go ahead and translate this over and perform our moment distribution. At this stage, you should have a good understanding of how these tables are run, including their carryover. So we won't go over that in great detail, but just be aware of the distribution factors and also the fixed end moments that are occurring at each of the joints. Once you run through that, we can solve for what the internal moments are at each of the joints. And this is not necessarily the answer to the final problem. This is for the problem where sway was restrained. What we are trying to analyze is this problem where sway is not restrained. So what we really are trying to get is, what is this force that is developing here due to the fact that I have restrained this? The way we're going to do this is we're going to take these moments that we have right here, and we will go ahead and translate those to the free body diagrams of the columns themselves. I'll go ahead and get those sketched on. To complete the free body diagrams, I need to make sure I've got the shears on here. And then I would run equilibrium to solve for the unknown shears. In particular, I'm concerned with the shears at the base. So if I sum moments at B, that will give me the shear at A, which would compute out to be 18.21 kips. So I can go ahead and write that in here. And for this other one, if I sum moments about point C, that will give me the shear at D, which is equal to 11.48 kips. So I'm going to come back here then, reminding you that we've got this restrained connection. We now know that the shear reaction down here is 18.21 kips. We know here it is 11.48 kips, and then summing forces in the x direction, including this, this, and this, I can then conclude that the reaction up here is 20.31 kips. So this looks like our original structure, except for the 20.31 kips up here. So we now want to shift gears and do an analysis of the frame where we have 20.31 kips here. If I can analyze this particular frame, superimpose it to this frame, then what happens is the 20.31 kips will disappear. So the process for that analysis is to put this restraint against sway on here, then grab it and pull it a unit displacement. In this case, we will displace it 1 inch. The idea here is we want to figure out what the reaction is here due to that unit displacement. And that will cause me to deflect its shape that looks something like this. So let's go ahead and analyze that. We will use the moment distribution method, so we will lock these members against rotation, and then I can find out what the fixed end moments are. I don't need to do the distribution factors again because I already have that. I know that this displacement here is 1 inch, and if I look at a beam chart, it tells me that the fixed end moments are computed as 6EI delta over L squared. So here's my fixed end moment, 6 EI times delta, which is 1, 240 inches squared. Now I got a little bit lazy, didn't write all the units on there, but everything was put in units of kips and inches. Therefore, there is no confusion as to what the units are that are coming out. So I know that's 900 kip inches. 900 kip inches. And I can then analyze the structure using moment distribution. Once again, handling the carryover and paying attention to where I got the fixed end moments placed in here along with the distribution factors. And this will give me what the moments are that developed here. I want to then take these moments that are in the columns, translate them over to a free body diagram, and then using very similar equilibrium as I did before, I can solve for the shear at each of these locations, transfer these known shear forces back over here, 4.69, 4.69. Remember, we had this locked up here, so running equilibrium, I know that in order to produce a 1 inch displacement up here, it's going to take 9.38 kips. Remember the structure I'm trying to analyze? I'm trying to analyze this one. So I know what force it takes to get a 1 inch displacement. I need to now look at what the response is when it's 20.31 kips. And so we'll recognize here that we've got this at 20.31, and then we've got this one here, 20.31, and we are going to superimpose these right here. So let me come back, get what the scale factor is. Scale factor is 20.31 kips divided by 9.38 kips. That will be 2.17. So I've got the responses for this. I'm now working on the responses for this, and I will add those two together, and here are the equations that develop because of that. So the moment at A, I take the response from the one that's restrained against sway, and I go ahead and take the moment that has the point load applied to it. I need to scale that up by 2.17, and that will be equal to negative 2,400 423 kip inches. I can continue. MB. That'll be 1610 kip inches. Then in a similar fashion, you get the rest of the internal moments. To conclude this example, let me just give a comment regarding the displacement at C. We come back here and remember that our total response is the summation of these two structures. And what we have found is that this displacement up here is 2.17 inches. So when you add that displacement to the displacement that's occurring here, the total displacement is 2.17 inches. That concludes this example. As always, it's a beautiful day for studying structures.